Hello, my name is Paul Schwarzmeier. I am a PhD student at TU Wien in Austria, and today I want to talk to you about climate change and my contribution to increase efficiency in industrial processes in order to reduce greenhouse gas emissions. But before I start with the actual content of my presentation, I want to give you a quick overview. After a short introduction including climate change, the motivation, and the industrial use case for my research, I will introduce you to the test rig of a packed bed thermal energy storage and a conceptual digital twin platform which I will use for my work. In the main part, the implementation part, I will talk about how we implemented the presented 5D digital twin platform for the lab scale test rig in more detail. With an exemplary workflow, I will demonstrate how the digital twin contributes to the optimal and reliable operation of the packed bed storage for the considered use case. I will close my presentation with a conclusion and an outlook including the main benefits of the proposed solutions for the considered use case and the possibilities which open up for future research. To reach the goals defined in the Paris Agreement, global CO2 emissions need to be reduced by more than 75% until the year 2050. More than 40% of the CO2 emissions in 2019 were emitted by the industry sector. Nevertheless, there are existing technologies and technologies in their research phase which show high potential to reduce CO2 emissions of industrial processes by a fair amount. As stated in the Arena World Energy Transition Outlook, 50% of the CO2 emissions in the industry sector can be reduced by the transition to renewables and the increase of energy efficiency. In most industrial processes, an increase of energy efficiency can be achieved by the reduction of primary energy consumption and the recovery of waste heat. The fact that the generation of heat is often accompanied with a high exergy loss makes the recovery of waste heat even more important. Let's consider a more tangible use case for this purpose. On this slide, the last few steps of a steel producing process, the so-called Linz-Donawitz or LD process, are depicted. The left side shows the current status of the process, which we will consider first. Besides the main product, steel, the LD process produces a considerable amount of slag and crucible gas. The crucible gas, which exits the process and is mainly composed of carbon dioxide and a considerable dust load, is utilized in a cooling chimney to produce process steam via radiative heat exchangers. Due to the high dust load of the crucible gas, convective heat exchangers would erode quickly, and therefore a further cooling can only be realized by injecting water in an evaporation cooler, which results in a substantial amount of waste heat. The idea to solve this issue is to replace the evaporation cooler with a packed bed thermal energy storage, which enables the storage and recovery of the waste heat in this process. In contrast to convective heat exchangers, the packed bed storage is insensitive to the high dust load of the process gas, and to make things even nicer, utilizes the slag produced by the LD process as storage material. With all these advantages and benefits, there are also considerable difficulties and challenges which arise when operating a thermal energy storage under such rough conditions. That's why the main focus lies on the implementation of a digital twin for a lab-scale packed bed storage, which will provide a platform for specialized services like fault detection algorithms and adaptive simulation models. Before I start with the implementation of the digital twin, I'm going to give you some detailed information about the test rig, which will be the physical entity of the digital twin. The packed bed thermal energy storage test rig, which was erected for this research project, consists of a cylindrical, slightly conical steel vessel with a diameter of 0.5 meters and a height of 2 meters. The maximum charging temperature of the test rig is 400 degrees Celsius. When charging and discharging the storage with a temperature difference of 300 degrees Celsius, the storage capacity is 50 kilowatt hours and the maximum power rates are 33 kilowatts. The storage tank, which has a volume of about 0.4 cubic meters, is filled with 900 kilograms of slag as storage material. The LD slag was chosen because it is a side product of the LD process and is therefore accompanied with zero costs, and additionally, the size, shape, and porosity of the LD slag makes it a very good storage material. To prepare the packed bed thermal energy storage for the deployment as a physical entity in a digital twin, it is equipped with 49 PT100 temperature sensors inside the packed bed. This multitude of sensors allows for a detailed estimation of the temperature field, especially the location and shape of the thermocline inside the packed bed storage. For the modeling of the digital twin, I will use the 5D digital twin framework proposed by Caspar. As the name indicates, this platform consists of 5 different parts, which are all connected to each other via a central connection hub. For reasons of time, I will not go into more detail here and refer to the publication of Caspar. Applied to the present use case, the packed bed test rig, the 5D framework can look something like this. Actually, this is the current status of our work, on which we will now take a closer look at. The physical entity consists of the packed bed thermal energy storage test rig, which is equipped with 49 temperature sensors. The SCADA system, which is also part of the 5D physical entity, consists of XAM control and a OPC UA aggregation server. XAM control is responsible for data acquisition and process control and hosts all the observed measurements to the aggregation server via OPC UA. The virtual entity consists of a three-dimensional thermal model of the packed bed storage. The model uses the finite element method and is based on the heat equation and other energy balances for losses and the energy in and outputs during charging and discharging of the storage. To increase the flexibility of the model, it is not designed as a 100% physical model, but as a hybrid model. This means that there are certain characteristic parameters like the heat capacity of the storage material or the heat transfer coefficient between the packed bed and the process gas, which can be adapted via data-driven methods. Additionally, the virtual entity also includes soft sensors. These are purely data-driven models, which are modeled and trained on demand based on runtime data and domain knowledge provided by the ontology. For the realization of the connection dimension, a MQTT message broker is chosen. MQTT is a topic-based publish-subscribe network protocol that enables the transportation of messages and data between devices, or in our case, the dimensions of the digital twin. Each of the other 4 dimensions and their subservices are connected to the broker as clients. Every client connected to the broker can subscribe and/or publish to different topics defined by the broker. The MQTT broker is responsible for receiving messages, filtering them, and sending them to subscribed clients. To allow subscribed clients to the proper processing of received messages, every publishing client has to follow a certain naming convention of the message payload. Integration and centralized storage of runtime data and domain knowledge, the next important dimension of the digital twin is the data dimension. In our case, the data dimension consists of a relational SQL database and 2 ontologies. The SQL database, the runtime data for the physical entity, and some important metrics like the power rate or the state of charge, which are calculated from the runtime data, are stored. Informations about the number of sensors and their location in the packed bed in relation to each other, and informations about certain events like the occurrence of an error are stored in the ontology in a machine-readable way. The ontologies also integrate runtime data from the SQL database via ontology-based data access. This allows for the other 4 dimensions and their subservices to access runtime data via semantic queries without having information about the structure of the relational database. The dimension of the digital twin, which is the service dimension, holds all the specialized services for the digital twin, which contribute to an enhanced operation of the physical entity. In the current status of the digital twin, the service dimension is composed of a data acquisition service, a soft sensor service, a prototype fault detection service, and a workflow engine. This service portfolio will be extended with further services in the future. For the management of the interaction and communication between all these services, the most important part of the service dimension is the workflow engine. The workflow engine can execute workflows which are defined and formulated in a graphical process flow language called BPMN. The workflow engine maps the topics defined by the MQTT broker to each other and executes services as it is formulated in the BPMN workflows. This way, services can be engineered and developed as standalone microservices independent of the rest of the framework. The only thing which is application specific is the naming convention of the MQTT broker. To point out the benefits of this implementation, I want to discuss a simple scenario. This scenario starts with the packed bed storage operating under normal conditions according to a schedule. This schedule is determined by an operational optimization service. The accuracy of the results of this optimization service strongly depends on the quality of the simulation models in the virtual entity and the state of charge estimation. Let's consider a scenario where a temperature sensor in the physical entity gets damaged and delivers a constant value of 0 degrees Celsius. This failure will lead to a significant error in the state of charge calculation, which propagates to following services and makes the output of the operational optimization inaccurate or even useless. To still maintain a proper operation and management of the storage, the measured value of the damaged sensor needs to be corrected as soon as possible. To do so, the three following services and workflows were defined. The first service and workflow is the data acquisition service/workflow. In the top part of this slide, the service workflow is notated as a BPMN diagram. This workflow is started when a message on the topic temperature sensor value is received by the MQTT broker. In the presented case, this message is published by the aggregation server. In the next step, the data acquisition service is executed as it is defined in the BPMN workflow. This service gets an array of real-time data via the payload of the MQTT message from the aggregation server. Before storing the received data in the Digital Twins database, the data acquisition service requests information about damaged sensors via a SPARQL query to the ontology. If the response of the ontology says that there is a damaged sensor, the data acquisition service fetches a soft sensor model for the damaged sensor from the virtual entity. It then overrides the measurement of the damaged sensor with the reproduced value from the soft sensor model and stores the preprocessed data in the Digital Twins database. After finishing all calculations and tasks, the data acquisition service publishes this information to the MQTT broker, which continues and ends its workflow. The next service and workflow I'm going to discuss is the fault detection service. In contrast to the data acquisition workflow, this workflow is started every 10 minutes by the workflow engine. As defined in this workflow, the fault detection service is triggered, which first fetches runtime data from the past 10 minutes via a SPARQL query to the ontology. The ontology provides this data, which is actually stored in the Digital Twins database via ontology-based data access. The fault detection service examines this data by utilizing classification algorithms. In case a damaged sensor is detected, this information is documented in the ontology by opening an error interval for the damaged sensor. When the fault detection task is finished and no failure could be detected, the workflow is ended directly, and in the other case, where the fault detection service classifies one temperature sensor as damaged, this information is published to the broker via MQTT message. This message just published by the fault detection workflow triggers the next workflow, which we called the soft sensor service/workflow. When an instant of this workflow is started, two different services and tasks are launched. The soft sensor modeling service and a pop-up on the operator screen with the request to exchange the damaged sensor at the next possible opportunity. The soft sensor service queries the ontology for information about the damaged sensor's location inside the packed bed and which other sensors are near the damaged sensor. Based on the information in the ontology's request and runtime data from the Digital Twins database, the soft sensor service starts the training of a regression model, which we call a soft sensor, and stores it in the virtual entity. This soft sensor can be used by other services to reproduce the true value of a damaged sensor based on the measurements of nearby sensors. After some time, when the machine operator changed the damaged sensor with a new one and completes the user tasks, the second branch of this workflow continues. This information about the newly installed sensor is transferred to the ontology by closing the error interval of the before damaged and now exchanged sensor. When both workflow branches have confirmed that they are done, the whole workflow is ended by the workflow engine. Of course, the tasks which were included in the presented scenario could also be done by one macro application that takes care of all the sub-tasks at once. The goal of this work, and in general of digital twins, is not to reinvent SCADA systems, but to provide a standardized and scalable platform for specialized services and application. The division of the digital twin into 5 dimensions allows experts from different areas to develop their services and models as independent micro-applications and to integrate them into a uniform framework via standardized interfaces. Expert knowledge of engineers and machine operators and information gathered from observing historic data can be centrally stored in the digital twin's data dimension via ontologies. The MQTT broker in the connection dimension enables the interaction of various services via standardized communication channel and supports the implementation of a workflow engine with its topic-based publish-subscribe functionality. Especially for the cooperation of experts in the field of computer engineering with experts in the field of thermal engineering, the service dimension with its main parts, the workflow engine, provides a perfect interface. The virtual representation of the physical entity in the virtual space in the form of models of different type and complexity lays a foundation for the extension of the digital twin service dimension with sophisticated methods and algorithms. Some examples which we will develop and investigate in future research are services for online model adaptation, which combines physical and data-driven modeling methods to keep models up to date, which is necessary for a proper storage management. Further, the use of transfer learning would allow the training of sophisticated classification models for fault detection in the virtual space and their deployment and utilization in the physical space. Another research focus will be the development of models for operational optimization, which benefit from the knowledge provided by the ontologies and the always up-to-date simulation models of the physical entity. For detailed information about the presented use case and the 5D twin platform, I refer to the conference paper Development of a Digital Twin Platform for Industrial Energy Systems, which will be published after this symposium in the conference proceedings. Before I finish my presentation, I want to thank you for your attention, and if you have any questions, please do not hesitate to contact me or Professor Hoffmann. Bye.